Hello, in this video we are going to derive Maxwell relations as well as calculation of Joule Thompson coefficients. So in this video we will talk about Maxwell relations in thermodynamics, and secondly we will talk about the calculation of Joule Thompson coefficient for real gas, and we will assume the model which is a van der Waals gas model. Now first of all, let us talk about how basic functions in thermodynamics are defined. So we know that G is defined as Gibbs energy function is defined as H minus Ts. So if we were to take derivative on both the sides, so I'll get dg will be equal to dH minus TdS minus S dt. Right? That is, what is G stand for? G stands for Gibbs energy function. H is enthalpy, T is a temperature, and S is the entropy of the system. Right? Further, we know that enthalpy we define as sum of internal energy plus pressure volume work energy. So if we differentiate this, so we get dH is equal to du plus pdv plus vdp. Call this as equation number 1 and this as equation number 2. Now over here, if I put the second equation dH expression over here, what do I get? I get dg is equal to, putting the expression for dH, du plus pdv plus vdp minus s minus sdt minus tds. Now over here we know that tds is nothing but q reversible. That is how the change in entropy is defined, dq, right? And from the first law of thermodynamics, we can cancel. We know that this dq will be equal to du plus pdv, right? The observer is outside the system. So from the first law of thermodynamics, we can see that these terms du, pdv and tds get cancelled. So from here we have the first expression, which is dg is equal to vdp minus s dt. That is the expression for change in Gibbs free energy. Now if we were to take the special cases, for example, under isothermal condition, we will say that since dt will be equal to 0, so dg would be equal to vdp. Right? So this is the first relation. Now we can also differentiate this, take a second derivative of it and then derive some more expression from here. As in, we can see that dg is a function of p and t. So Gibbs free energy is a function of p and t. So the total derivative, if we were to write the expression for total derivative, which is dg, that would be partial derivative of g with respect to p at constant temperature times dp plus partial derivative of Gibbs free energy with respect to temperature at constant pressure times dt. And if we were to compare with this expression, so I can see that del g by del p at constant t would be equal to v. Also del g by del t at constant p is equal to minus s. Now what we can do, we can take a second derivative and from there we can, from equivalence we can get further formulations also. For example, the first, if I differentiate this with respect to T at constant pressure, the first one we differentiate with respect to T at constant P. So what do I get? I get dou by dou T operator at constant P, we are differentiating dG by dP at constant temperature, so that will be equal to del of V by del of T at constant pressure. Call this as 1. And if I differentiate the second with respect to P at constant T, so what do I get? I will get dou by dou P at constant T, differential of dG by dt at constant P should be equal to minus del S by del P at constant T. This is second. So we can see that the left hand side operators are same. Okay, so we can see the equivalence coming from here. So further we can say for this expression we can have this Maxwell relation, and that can be that minus dou S by dou P at constant T is equal to del V by del T at constant P. So this is the kind of relation that you can have from the constant variable notations, right? Equating to the total derivative form. So this is the expression for the Maxwell relation for dG, which is V dP minus S dt. Okay, similarly if we were to write for del H, we can do so. What we have to do is we will just write the expression. You can see from here that dG is equal to V dP minus S dt that we have proved. So if we were to put this dG expression over here, we will get the expression for dH on reorganization of this equation. So dH will be equal to TdS plus VdP, right? That is the second Maxwell relation. Got this? Further, we can also try to derive the expression for du. That is, the terms that we have cancelled in this equation, we can take that, and from here we can say that du will be equal to PdV, minus PdV plus TdS. So these are the Maxwell relations. Next, our effort would be the calculation of a Joule Thompson coefficient. Now, first of all, we will have to understand what is Joule Thompson expansion. So when we say Joule Thompson coefficient, so we are talking about the Joule Thompson expansion. So Joule Thompson expansion is basically isenthalpic process. It is isenthalpic process. So we have a gas contained and we expand this through a valve, right, maintaining a constant enthalpy. So it is basically adiabatic insulation which is there between system and surrounding, right? So it is basically expansion keeping enthalpy constant. So H1 will be equal to H2, which means U1 plus P1 PV1 will be equal to U2 plus PV2. So if you are doing expansion, then the work would be done at the expense of internal energy, and we would always see that if the work is done at the expense of internal energy, we would conclude that it should always cool. But that is not the case. For some real gas like hydrogen and helium, what happens is when you have this expansion, the temperature actually increases and not decreases. So we first define the Joule Thompson coefficient, which is mu Jt, and how we define this as, that is basically change of temperature with pressure keeping enthalpy constant. This is how we define the Joule Thompson coefficient. This is Joule Thompson coefficient. Now we have to derive the expression for real gas. We know that Joule Thompson coefficient for real gas mu Jt, that is equal to 1 upon Cp. This is 2A upon RT minus B. So this is what we need to prove. So derivation is a bit tedious, but do all the steps step by step, and I hope that you will be able to solve it. So how we have defined? We have defined this as a isenthalpic process. So when we say isenthalpic process, then the change in enthalpy would be 0. Enthalpy is function of pressure and temperature. So total derivative I can write as partial derivative del H by del P at constant T times dP plus del H by del T at constant P times dt. For the process, because it is isenthalpic, so we know dH is equal to 0. So if we equate that, so from here you can see that del H by del P at constant T times dP is equal to minus del H by del T at constant P times dt. Right? Now if I divide both the side by delta P or dP at a constant H, at constant enthalpy, so what do we get? You would see that this would further give us del H by del P at constant T will be equal to del H by del T at constant P into del T by del P at constant H. Now if you were to see very clearly, we have two terms. Del H by del T at constant P is nothing but Cp, and del T by del P at constant H is mu Jt that we have to find. So this is the first step of the derivation. We'll continue this in the next slide. So what we have got on rearrangement, you can always stop the video and get back to the back slide and see the expression, write it, and then continue with the derivation forward. So that is equal to minus del H by del P at constant T upon Cp. So we have to find expression for del H by del P at constant T. So now we know from the Maxwell relation that we have derived, we know dH is equal to TdS plus VdP. So if I divide this expression by dP at constant T, I get del H by del P at constant T would be equal to T del S by del P at constant T plus V. Now if you remember, we had derived this constraint variable notation on the first slide, and it was del S by del P at constant T was equal to del V by del T at constant P. If at any point of time you get confused in derivation, you can always go back to the previous step. And I would maintain that you keep on writing simultaneously in your copy as you are doing this derivation. So we can replace this term by this value. So we know that del H by del P at constant T would be nothing but it would be V minus, if I just put the value, V minus in place of this T dV, del V by del T at constant P. Right? This is the expression which is required over here. I hope that you are continuing along with me and deriving this step by step. So this is what we have to calculate, and we will do it for the real gas. The real gas model that we take into account is the van der Waals model, for which for 1 mole we have the equation P plus A by V square into V minus B is equal to RT. Right? Okay. So this is the van der Waals equation, where A stands for it's indicate the magnitude of intermolecular forces and B tells you about the molecular size. Right. So if we were to rearrange this, and you can do so, you can pause the video and rearrange this, you will get V is equal to RT upon P plus B minus A upon PV plus AB upon PV square. This is just on rearrangement of this. Now if you were to see the expression over here, the last term A is very small in magnitude as compared to PV. Also AB would be very small. Multiplication of the van der Waals constant would be a very small value. So for the last two equation, if I were to write PV as RT, the error that we will get is negligible. but that will help us in derivation. So what I am doing is, here the last term I am multiplying by p, so it becomes p square v square, and everywhere I am replacing pv by rt. This is what I am trying to do. Okay, continuing the derivation in the next slide. So on putting that value, v comes out to be rt upon p plus b minus a upon rt plus abp upon r square t square. Now if we differentiate this, because that is what we require in calculation of a Joule Thompson coefficient, this is r by p plus 0 because b is a constant plus a upon rt square minus 2abp upon this is r square into t cube. Okay, now r by p we will take from the van der Waal equation. R by p will be taken from the van der Waal equation. So if you rearrange, you can stop the video and do this step additionally in your copies. So r by p from van der Waal equation we get as v minus b by t plus a upon rt square minus abp upon r square into t cube. Now those who are worried about from where this has come from rearrangement of the van der Waal equation. Van der Waal equation is p plus a by v square into v minus b is equal to rt, right? You can take p common and then you can just put it on the right hand side and take r by p as a left hand side variable. The expression that you get on the right hand side is this. Okay. Now this is what we put in this derivative expression, partial derivative expression. So here we get del v by del t at constant p would be equal to, we'll be putting this, right? So we have v minus, we can just put the value v minus b by t plus a upon rt square minus abp upon r square t cube. This is the value of r by p, and the remaining expression we just write as it is. So you can see this is the expression that I am getting, which is equal to v minus b by t plus 2a upon rt square minus 3abp upon r square t cube. Okay, that is the value of this partial derivative. Now we just need to put this in our calculation of Joule Thompson coefficient. If you remember, let's recall what we were supposed to do. We were supposed to find value of mu jt, that is nothing but 1 upon cp. This is t times dou v by dou t at constant p, which we have found, minus v. So what I am doing is I am just putting this expression for del v by del t at constant p in that calculation of mu jt, right, which I am trying to write in the next equation. So if I just put it over here and rearrange, I get mu jt is equal to 1 upon cp, and this would be t times, and this entire expression that we have in bracket, which is v minus b by t plus 2a upon rt square minus 3abp upon r square t cube, okay, plus v. So if you rearrange, you can pause the video and do this intermediate steps. So you will get mu jt Joule Thompson coefficient as 1 upon cp times 2a upon rt minus b minus 3abp upon r square into t cube. This is the expression that we finally get. Now generally just this Joule Thompson coefficient, I mean Joule Thompson expansion, is carried out at low pressure and high temperature. So we can see that p upon t cube will be a negligible value, so we can neglect the last term, and therefore for real gas we can assume that Joule Thompson coefficient is nothing but 1 upon cp into 2a upon rt minus b. Right, now this explains that for Joule Thompson coefficient to be positive and negative, the values of this first expression and second expression does play a role. Right, now understand mu jt is defined as what? That is del t by del p, change in temperature with pressure at constant enthalpy. Now if it is a expansion, then delta P will be negative because pressure would decrease. And if for a gas mu Jt is Joule Thompson coefficient is less than 0, then the sign of delta T should be opposite to. If pressure is decreasing, then temperature would be increasing. So for the gases where mu Jt is less than 0, the temperature actually increases, right? And if for a certain gases mu Jt is more than 0, with the expansion, that is pressure decreasing, the temperature would also decrease. So for hydrogen and helium, we can see that A upon RT, these terms are very less. And therefore, for those gases, mu Jt is less than 0. And therefore, these gases heats when you do Joule Thompson expansion, which is also known as a throttling process. Now over here, one thing more I want to say is that for a same gas, mu Jt, for same gas, mu Jt, which is earlier more than 0, after a certain temperature, this becomes mu Jt becomes less than 0, which means the nature of the gas changes after a particular temperature, and that temperature is known as inversion temperature and denoted by Ti. I am writing it over here. So inversion temperature is where the nature of gas change, which means mu Jt, which was earlier, we can say more than 0, after this temperature, Joule Thompson coefficient becomes less than 0. And how we are supposed to calculate that? So mu Jt expression is 1 upon Cp. This is 2A upon RT minus B. So equate this term to be 0. So on equating this term to be 0, I get inversion temperature as 2A upon RB, and which we can see is twice of the Boyle's temperature. Okay, so this was a simple derivation for the Joule Thompson coefficient.